Okay, so how to distinguish the white pieces from the black ones when you're writing a chess program. So you want to pick up only those pieces that belong to the side to move, and if you have an appropriate piece encoding, then it's the matter of a single bitwise operation. So let's have a look how it works on the example. So here I have the source code split it into two parts. So here I have the 0-page board representation and two variables, the constant to distinguish the onboard square from the offboard ones, and the side to move, which is absolutely essential. So if I assemble this, and I want to assemble this at the origin of 0 because that's where it's supposed to be, and upload, and we get the bytes now. So we have a look at the hex dump from 0 to 0x90, so this would be the chessboard plus one extra row to show the variables, and column 16 sorry, and here is the chessboard. So yeah, here it is, starting from here. So we have the black pieces on top and the white pieces in the bottom. So here is the p-square table, so you don't really need to get distracted by this part. So this is what we're interested in, 64 by 64 squares. And here is the constant to distinguish the onboard squares from the offboard ones, which we've covered in the previous video. And here is the side to move. So this is the most essential thing. Now, first, probably I will demonstrate how the distinguishing on its own is actually working. So we'll first pick only white pieces if the side to move is white, and then, well, I set this constant, this variable from white to black, then we'll pick up only this pieces. And since we don't really have some debugging features here other than inspecting the hex dump, in this case one emulator I made, so we're just going to be marking the pieces with the FF, with the byte FF, just to make sure that we do traverse the exact squares and sort of picking up the piece there to generate the move offsets for. All right, so here is the initial state of the chessboard, and if I now go to the main program part and copy and paste and assemble, this time I want to load this at the origin to hundreds hexadecimal. So let's start by actually running this. So 0200 0200 and upload. All right, and I just run the program. So I just ran the program, and let's go back to the hex dump. So from 0 to 0x90, 16 columns, and suddenly you see like all the white pieces has been marked with FFs, which means that we did distinguish the white pieces from all of the pieces on the chessboard, because we have the white. Here we have the byte representing the white to move, right? Now if we just change this byte to the black side to move and do this and run the same code, in this case we'll pick up the black pieces. So let's have a look how that works as well. But before that, I obviously need to upload the board again. So let's have a look at the hex dump again. 0 0x19, 16 columns. So I just restored the original state, right? Now we need to go to this byte and change it. So now let's go to, so I'm going to addressing mode, 0080, and here is the hexadecimal 88 constant, and the next one is the side to move. So here I want to set the side to move equal to black, and this is going to be 10 hexadecimal. Going back to addressing mode, and go into 0200 and run again, and then have a look at the hex dump one more time, one last time. So from 0 to 0x19, 16 columns, and here we go. So we just picked up only black pieces to move, which means that from now on we can generate moves only for black pieces. And here is the value for that represents that it's the black's turn to move. Now let's have a look at the source code, just to figure out how simple this is, and we actually need the only bitwise operation to perform this trick. So I'm going to the file with the chess program itself, right? So I've edited the commentaries from the last video, so for those of you who's not aware what the heck is this is the 6502 assembly, right? So once we made sure that the square is on board, we actually load this square, load whatever we have the board indexed by X register, and X stands for the for the source square, where the like the square occupied by the piece. And for now, I think that it would be just fine to have like A register containing the piece, X register containing the source square, and Y register containing the target square, where like so X and Y would be like the source and target square for the current move to make. And here the Y register for now has this constant of FF just to serve as a marker, has been demonstrated. So if we have look here, so if I look at this code, so we're loading to the A register, loading the whatever we have at the board indexed by X, by the source square. So literally A register now contains the piece code after this operation. And now we just need to bitwise end with the side to move. Well, the side is it's a variable. Well, it's just a definition. So it gets replaced by the constant of 81, and 81 is whatever we have at this byte, right? So if this is 8, then it's white to move. Otherwise, it's black to move. And in case if after performing this operation, if the 0 flag has not been set, right? So we have this branch not equals condition, and we're going to the loop over the move offsets, and here is the loop. It's not implemented yet, it just skips to the next square and makes this and marks all the pieces we've traversed with the FFs. So just to give user an idea that we did properly distinguish between the pieces. So this is how elegantly and how very minimalist implementation as well. So it's both elegant and minimalist. So now to make it work, we need the specific piece codes for all the pieces. So let's have a look at the piece encoding that actually provides this elegant implementation for distinguishing the white pieces from the black ones. So, and by the way, yeah, it's not tied up to the 6502 assembly. You can implement this in whatever language. That's obviously that's obvious. I'm not even talking about because that's obvious. So the rightmost 3 bits represent the piece type. And well, currently I have the upstream in pawn and the downstream in pawn being as a different piece types. I'm not sure if I'm about to be keeping this further on. Maybe I would slightly change this. Maybe I didn't take a decision yet, so how exactly I'm going to be proceeding with this sort of a thing. It's a little bit unclear at the moment. But anyway, the rightmost 3 bits represent the piece type, right? And here we have the color. So this is the bit that is worth 8, and this is the bit that is worth decimal 16 or hexadecimal 10. And this is how it works. So you see, like here, if we convert this, so you just see this 4 digits, then 1, and this 3, it's also 4 digits. So this 4 digits, and then this 1, and this 3 is also 4 digits. So in a hexadecimal, 4 binary digits are represented by a single hexadecimal digit. So this 4 goes here, and this 4 goes here, right? And if we have a look at this, the first column, we have zeros right over in here, and we have ones right over in here. And that's the exact reason why if we bitwise AND, we do perform the bitwise AND operation of whatever piece we have. So let's say we have this, so let's say we have this white pawn, and here, so if this, just to give you an idea, so if let's say 0, 9, so just to make it in a binary form. So we want to bitwise AND this with a constant, with a white to move, and the white to move is going to be 0, 0, 0, 1, 0, 0, 0. Then what should be here? So it's gonna be 8, right? So like this, 1 and 1, 1, and the rest are zeros. And this is going to be 8 in decimal and in hexadecimal as well. And it's not 0, hence the 0 flag is not set, hence this branch not equals actually works. So yeah, we have 8 here, So yeah, we know that this is the white piece, and just to give you an idea in regards to how this works with the black pieces. So for instance, let's take the black bishop. So here 001 and 50101, and we want to bitwise end this with 16. With 16 in decimal, with 10 in hexadecimal. Okay, so 1 and 0. So what we're gonna have here, so 0 0 0, then 1 bitwise end with 1 is gonna be 1, and here all the rest would be zeros, and this is gonna be decimal 16 or hexadecimal 10. So that's definitely not a 0 as well. So again, like this branch not equals in the source code works perfectly well. So this is pretty much all about it, and yeah, that's all I wanted to show you guys. So this is how simply and how elegantly we can distinguish the white pieces from the black ones while writing a chess engine. Again, like, this can be done in whatever programming language. I'm just doing this in 652 assembly because I want to come up with the most minimalist chess program possible in terms of bytes being involved within the binary executable. Because for me personally, that's the true minimalism. So yeah, this is it from my side. Thanks for watching. Until next time, and take care.